Good day, everyone, and welcome to today's DevOps.com webinar. We're excited that you've joined us. The topic is a really interesting one. 3 pillars, 0 answers, rethinking observability. It's a hot topic. Our webinar today is sponsored by Lightstep. My name is Mitch Ashley. I'll serve as your host and moderator. A few housekeeping items. We are recording the webinar, and all participants will receive an email with a link to the recording as well as a copy of the slides. We're also giving away 3 $50 Amazon gift cards, so please stick around to the end of the webinar and find out who got selected at random. Now, our speaker is a fantastic speaker today, and I know that she loves questions, so we'd love to have you enter your questions into the GoToWebinar control panel, and do that anytime during the presentation. We'll get to the Q&A section of the presentation later in the hour. So let's move on to our topic, 3 pillars, 0 answers, rethinking observability. It's my great pleasure to introduce today's featured speaker, Katia Bazzi, who is software engineer with Lightstep. Katia, really excited to hear your presentation. I'm gonna hand the baton over to you and let you take it away.
Thanks, Mitch. Hi, everyone. My name is Katia Bazzi. I am a software engineer at Lightstep. I work on a team where I spend most of my time working on the backend distributed system at Lightstep, which powers a number of aggregate trace analysis features, which help other software engineers quickly debug regressions in their system. And I've been here about 2.5 years. It's been super exciting, and I've gotten an opportunity to learn a lot about the observability space in that time. So today I'm here to talk about observability. There is a lot of discussion about what that term means and how we can establish an effective practice around observability. This talk is based on a blog post and talk given by Lightstep's CEO, Ben Sigelman. He has been fearlessly leading our company for the last 5 years or so, and before that, he was at Google working on the Dapper project, which is something I'm going to reference a couple of times throughout this talk. So this talk is intended to be a thought piece for us to reconsider how we execute our observability practice and how we evaluate observability technologies in the space today. And so it's really broken up into 2 parts. The first part of this talk is going to be a critique of how we currently evaluate observability through the traditional 3 pillars of observability. The second part of this talk is going to be an alternate scorecard that we can use to evaluate observability tools and technology. So let's dive right into the critique of the 3 pillars. So there is a bunch of conventional wisdom out there. Currently, we know that observing microservices is really difficult. Any software engineer who has written or deployed microservices knows that this is true. I personally have experienced this pain point a lot throughout my career. There's also this perception that large companies like Google and Facebook have actually solved this problem. They've figured out how to effectively observe microservices. And the way that they do this is by using metrics, logging, and distributed tracing. So since they've solved observability through these 3 tools, we should as well. And that's essentially the essence of the 3 pillars argument. It's not really something that I personally agree with, or a lot of my coworkers at Lightstep agree with as well. It's not really based on a first principles understanding, and we don't really think that we should be following the footsteps of these larger companies that have to deal with huge amounts of scale, because a lot of the tools that are useful at that scale are not necessarily useful at all the other scales that a lot of technologies have in the industry. Specifically, Google is processing 5 billion RPCs per second, and if you're going to build an observability system that handles 5 billion RPCs per second, there's going to be this natural tension between scale and feature set, and naturally you're going to have to give up a lot of features to accommodate for that sort of scale. the solutions outside of the Facebooks and the Googles are oftentimes a lot more powerful in terms of the feature set because we don't have to worry about scaling to 5 billion RPCs per second. So here are the 3 pillars of observability. If you somehow set up metrics, logging, distributed tracing, all of your problems will be solved, but that's not necessarily true. And that's gonna be what I'm gonna discuss in the first half of this talk. The first half of this talk will mostly be about the flaws in each of these pillars and why just setting them up alone isn't sufficient. So before I dive into the flaws of these 3 pillars, I wanted to give a quick overview of what metrics, logging, and tracing actually means. So here are some metrics. These are from our internal system at Lightstep. They're a bunch of squiggly lines. So essentially what you have here is like some statistics. You sample those statistics at some frequency and you draw lines between those samples and you get metrics like this. So these are metrics. I think a lot of software engineers are familiar with them now, and they're used quite commonly. The next pillar in observability is logging. So here you can see an example of some logs. Once again, I think a lot of software engineers have a firm understanding of this. You essentially have statements in your code that emit structured or unstructured data to a log file, which is centralized. You can then query in that log file and generate a list of logs that are interesting to you, and you can also get some very basic statistics from those logs. So that's logging in a nutshell. And then the last pillar of observability is distributed tracing. So tracing usually looks like something like this. This is a screenshot of Zipkin. There are a number of other distributed tracing tools out there, but the visualizations all commonly look like this. The common elements here is there is a timeline, and there are different horizontal bars here that represent a different unit of work in a distributed system. And you can essentially understand how a transaction propagates through a distributed system across different service boundaries. And you can also understand the critical path of a trace more easily here. So that's tracing in a nutshell as well. So in Ben Sigelman's original talk, he talked about how like why people have latched on to this concept of 3 pillars, and like one potential theory is that human beings really like to think of things in threes. You can see that the Rice Krispies have 3 different characters, like there are 3 flavors of ice cream that are super common, and the 3 Stooges gained a lot of popularity. But more seriously, software engineers, I feel like, are very data-driven, and they're also really frustrated with the promise of observability tools that exist right now. The use cases and value prop just simply isn't there for a lot of tools that exist in our industry today. So since we're data-driven software engineers, we really want a factual evaluation of these technologies. So it's easy for us to ask different observability tools if they support metrics, or if they support logging, or if they support tracing. So that's really, I think, why the 3 pillars has gained a lot of popularity and has caught on so much. But we think that we can grade observability solutions in a more sophisticated way than this. So now that I've talked about what tracing and logging and metrics actually are, we can maybe go through the fatal flaws that exist for these different pillars. So first, let's talk about metrics. So here you have an example of a time series or a metric, and this is a real example from one of Lightstep's internal systems. And it's pretty obvious that an anomaly happened around 1 p.m. So you can see that spike around 1 p.m. And the question here is, what happened at 1 p.m.? Why is there an anomaly at this time? We also have this concept of tags or dimensions, which can help explain variance in time series data. And so you can group by that tag and get a new set of lines. And each line here represents a different tag value. And so then you can quickly identify that one of the tag values is highly correlated with that anomaly. This doesn't give you the root cause necessarily of the anomaly, but it gives you pretty useful information. And so this is really a great way to debug a regression through metrics. But the problem here is that the number of values for a tag can get really high. So some common examples of tags are like globally unique identifiers, or like user IDs, and those have a huge number of possible values, and that can get really expensive, and that's called cardinality. So cardinality is essentially the number of values for a tag. So if there are a large number of values, that means that there is a high amount of cardinality for a particular tag. This cardinality issue is really a significant pain point for metrics, and it's been a centerpiece for a lot of product marketing for a lot of companies. And there's not an easy solution right now. Like it's just getting like pretty expensive. So that's the fatal flaw with metrics, is that cardinality can be quite expensive. Now let's move on to the fatal flaw of logging. So logging is really also quite expensive just because of the cost of the data itself. So when we were dealing with a monolith, it was already really expensive to log, whether we were spending money on Splunk or Elastic clusters. We had some constant number of log statements per transaction, and those log statements were still getting pretty fairly pricey. And in the distributed service world, it's actually even more expensive because of the number of microservices that we have to deploy now. So if you look at this visualization, you can see that these different boxes represent different services, and these dotted red lines here represent a transaction as it traverses through many service boundaries, which is what modern systems look like today. So if you want to use logging to understand these transactions, now we have to log at each entry point and each exit point for each service, or at each ingress and egress operation for each service. So instead of having that constant number of logging statements per transaction in the monolith, we are now taking our transaction rate and we're multiplying it by the number of microservices, which is pretty expensive, and end users actually don't realize that your backend is a microservice architecture versus a monolith architecture. So the cost of the logging is scaling with the number of microservices, but your value to the end user is not increasing at all. So you take the transaction rate and you multiply it by the number of microservices, and then you have to multiply it by the cost of network and storage, and then multiply it by the cost of the number of weeks of retention, and that just results in a lot of money. So the sheer cost of this data volume is the major flaw for logging. And lastly, we have a fatal flaw in tracing as well. So the CEO of Lightstep, Ben Sigelman, worked on Dapper at Google, and Google spinned up this project because of how expensive logging could be. So instead of sampling every log statement, Google decided through Dapper to sample every transaction, and they would decide if they want to either keep or discard the entire transaction. So you can see here what they ended up doing is they we're able to significantly reduce the cost of getting this data out of process and into regional storage by only keeping 1 in 1,000 transactions. And then they had to do another 10x estimation of that data to get into truly globally centralized storage. So at the end of the day, they only kept 1 in every 10,000 transactions, and the other 9,999 transactions were discarded. And this is a huge problem because mostly because an anomaly by definition is doesn't happen very often, and if you're discarding 9,999 transactions, you likely won't identify that needle in a haystack, which is fairly problematic. And you're also not able to perform aggregate analysis focused on a particular aspect of your system. So Dapper itself was really useful for high throughput products like web search at Google, but for lower throughput products like Google Checkout or spreadsheets, it had limited value because they threw out so much of the data. And for a lot of applications outside of Google at other technology companies, it's meaningless to have just 1 in 10,000 transactions. And you're also really not able to make meaningful statistical statements about these systems. So that's the primary flaw with distributed tracing. So here's a quick summary of the fatal flaws of logs, metrics, and distributed tracing. It's really impossible to find a solution that implements logs, tracing, and metrics that 1, scales gracefully, 2, accounts for all data, and 3, is immune to cardinality issues. And this is the crux of the critique of the 3 pillars, is that just implementing these 3 solutions is not enough. And there are a number of companies who have implemented these 3 pillars and are still feeling a lot of pain. So we as an industry should be smarter about how we evaluate observability and really come to terms with the fact that it's not just these 3 checkboxes. It's not enough. And like we can use more sophisticated tools. So there's no silver bullet. Something else I wanted to talk about quickly is there should really be a larger distinction in observability between data and UI. So like if you go to google.com and you search for a computer, you end up seeing a bunch of results that show you a monitor, but a monitor isn't actually a computer, it's just the UI. And that argument really resonates with me when it comes to the data in like the data such as metrics, logs, and tracing compared to the visualizations of that data. So you can see here that logging and tracing data can be used to generate time series, but traces are really just a specialized form of logging. And there are all other types of visualizations that have nothing to do with these 3 pieces of data that we can come up with to help us in the observability space. So it's really important to distinguish between collecting the data and consuming the data in a reasonable way. So once again, metrics, logs, and traces are just data. They're not a feature, they're not a use case, they're just data. And if we can collect all of this data, but if we're not intelligent about how we consume the data, it's not particularly useful. So the second part of the talk is offering an alternative to the 3 pillars. So introducing a new scorecard for observability. Before we dive into what the scorecard actually looks like, I think it's important to define what goals and activities are. So goals are related to how our services perform in the eyes of our consumers. Everything should take a service-centric view in the DevOps world because at the end of the day, all of the consumers here care about the goals of their particular services. We should also think about how the activities that we take as operators accomplish those goals or further those goals. So we can really divide observability into these two core pieces. What are the goals of my service, and what are the activities that I need to take in service of those goals? And here's a quick vocabulary refresher before we dive into the scorecard. Many of you may be familiar with what an SLI is, but if you're not, it's a service level indicator. It's referenced in the Google SRE book where they talk about SLOs, SLIs, etc. But an SLI is an indicator of health that a service's consumers would care about. It's not an indicator of the service's inner workings, and that's an important distinction to make. So for example, if you have a Kafka queue, an SLI might be how long it takes to get a message into and out of the queue for a particular topic. But you wouldn't necessarily want to look at the CPU load or the number of nodes you are running as an SLI. That just shows you the inner workings of how Kafka is run. So that's the main distinction. And something else that's useful with SLIs is there's not that many of them usually. There's only a few of them that really do matter. And if you're working on an optimization for your service and you're not moving an SLI significantly, then the optimization may not necessarily be worth making. So SLIs are really useful in guiding consumers into running high-performing services. So in observability, we've talked about the mental model of having goals and activities in service of those goals. And the two major goals in observability are the following. Firstly, we, as software engineers, want to gradually improve a particular SLI. And we also sometimes need to rapidly restore an SLI. So an example of gradually improving an SLI is if your product manager comes up to you and tells you that the product is way too slow, then you would probably take on a project to gradually improve the SLI of several services, and you may need to do a series of optimizations and refactor those services in order to meet that SLI and improve the baseline. On the other hand, you might have to, once in a while, rapidly restore an SLI. So what this looks like is if you have an SLI that's essentially at steady state for a long time, and then all of a sudden there's a huge spike and you have to fix it as soon as possible. And this usually takes the form of identifying something that you have to undo, like a release, for example, or a feature flag switch. This is also kind of the goal that you have when you're woken up in the middle of the night and you're paged about something as well. So it's important to identify which goal you're trying to achieve when you're thinking through different observability tools, because these two goals have different workflows, and that's important to recognize. In the first goal, you may spend days, weeks, months optimizing the SLI, whereas the second goal has to happen as soon as possible. So you have to fix it like immediately. And those are both quite different workflows. So we've already talked about the goals that consumers of services have. The next part here is talking about the two fundamental activities that these consumers take in service of those goals. So the first activity is detection, and that usually takes the form of measuring an SLI precisely. So some examples of this are looking at dashboards that show you the P99 latency or the throughput or the error rate of a particular ingress operation. So that's usually what detection looks like, is you want to detect when an SLI regresses easily. The second activity that is quite fundamental here is refinement, and refinement involves reducing the search space for plausible explanations. So if you detect an SLI regression has occurred, then you want to easily refine your search space for hypotheses that may explain that detection. So before we dive into the scorecards for these two fundamental activities, I wanted to give a quick interlude about statistical frequency. So these 4 graphs show exactly the same data. They show, I think, P99 data of some signal. But the main difference between these 4 graphs, going from the top left to the bottom right, is that they have different levels of granularity. So the top left shows 1 second granularity, then 5 second, then 10 second, and then 25 second granularity. And you can see that as you smooth over longer intervals, you're not able to see some interesting outliers. Specifically, in the bottom right P99 time series, you can't really tell if this regression here is a steady state regression or if it's an intermittent regression. Whereas if you look at the first time series that has a much smaller level of granularity, the 1 second time interval, then it's much clearer that something intermittent is happening, and that's causing the particular incident. And identifying whether or not the regression is intermittent versus steady state is a pretty important clue in this debugging process. So I'll revisit why this is important in the next slide, but just keep in mind what the difference is between the different granularities. So let's dive into the scorecard for detection. So here is the scorecard for detection. If you buy the argument earlier that observability is about detection and refinement, then we can dive into what the scorecards for those two activities looks like. So for detection, it's really important to understand the cost of cardinality, and it also helps in understanding if a particular tag is correlated with a regression, which I was showing you guys earlier through metrics. So a lot of people make it out to be that cardinality is too expensive to pay for, and I don't think that's true. I think we should pay for cardinality at some level, but we just need to understand how much it's going to cost because it can get out of hand really quickly. The second piece here under specificity is stack support. So it's important to understand what stacks are supported. Specifically, can you go up into the mobile and web stack with the same solution that you're measuring your internal services? If you're planning on improving end user latency, it's important to be able to measure all parts of the stack so that your end users have a good product experience. Similarly, are you able to go in below your application code into your open source dependencies or your managed services and get a sense of how failures at that layer are propagating upwards into your application code? So specificity here is mostly about understanding cardinality and your stack support. Fidelity is around mostly around correct statistics, and there's a lot of exclamation points here because it's very common for P95s and P99s in observability tools to be inaccurate. So one thing that I've seen frequently in other observability technologies is that they will take a P99 value from each host and then average them. And statistically, that's meaningless. That's not the true P99, and a lot of people don't realize that. So if you are measuring P99, that's awesome. That's a really great way to understand the outliers in your system. But you should really be careful about statistics because a lot of the times you're not truly looking at a P99 value. The other part of fidelity here is the high stats frequency. So that was what I was illustrating in the previous slide. For detection to work really well, you really want to be able to detect the difference between an intermittent and steady state failure. And that's much easier to do if you have the high frequency data. So if you have the 1 second granularity versus the 25-second granularity. So it's important to evaluate whether or not you have that so that you can quickly detect the difference between an intermittent and steady state failure. Lastly, Freshness is also fairly important in detection. If you ever want to do a real-time analysis of your system, you need to make sure that you're investing in a technology that will give you a small lag between what's happening in your system and what's happening on your screen. So ideally, you have a real-time observability solution in terms of seconds, not in terms of minutes. So I wanted to quickly talk about why refinement is important before we dive into the scorecard for refinement and why we shouldn't measure something else. So as you can see here in this graph, the x-axis represents the number of microservices, and you can see that as you add more and more microservices, the number of things that your users actually care about doesn't change. I was referencing this earlier in the talk, but your users don't care if you have a distributed architecture or if you have a monolith. They really just want to achieve whatever they want to achieve in the product in a reasonable way. What's also interesting here is as you add more microservices, the number of failure modes increases linearly. And that's just because service-to-service interactions introduce all sorts of ways for things to break, and many of them are really hard to predict. And these are problems that we didn't really have to deal with in the monolith world, and now we have to deal with a much higher number of failure modes in the microservice world. So this is problematic because the number of failure modes are increasing, but the number of things that our users actually care about is remaining the same. And even if we could build a dashboard that had every possible failure mode on it, we don't have time as human beings to sort through all of that. It's a lot of the times when one service is experiencing a failure, you'll see that failure crop up in a number of other services concurrently. So you'll see a bunch of lines that are spiking at the same time, and you're left to guess which service is actually the culprit, and you have to do some elaborate linear search to identify that, which is really, really painful. I've seen a lot of dashboards with a ton of spark lines, and I've also seen those dashboards during an outage, and in my mind those dashboards are just totally inactionable. There's really not a good way for me to reduce the search space with those different failure modes. So that's why refinement is so important here. We don't really have time to elaborate over all of the different failure modes and figure out whether or not a failure mode is a problem. We have to figure out instead how to reduce the search space. Specifically, we're not really gonna have a observability solution that tells us what the answer is during an incident. Instead, I think the expectation we should have around observability tools is they should help us reduce the search space and refine it down to a set of hypotheses that are actually credible and actionable. And that's really the crux of it here. So here's what the refinement process usually looks like. Typically, you discover a variance in your system. This could be an increase in error rate, for example, and then you go and try to explain the variance with observability tools. And this usually takes the form of identifying new variants, which you then have to explain again. So you're doing this loop for a while until you can identify a fix that you can implement. And that could be rolling back the release or adding caching, etc. And then that's when you can go and you can deploy the fix. So we're consistently looking for a variance that can be explained by a problem that we know how to solve. I also wanted to quickly discuss histograms because I think that's pretty important in the refinement of the latency search space. So here you can see a histogram. This is a screenshot of the Lightstep product. And this is a histogram for latency of a particular request. So the x-axis here represents slowness. So the further right that you go, the slower that you go. And the y-axis here represents frequency. So the further up you go, the more data there is. And you can see that there is a P99 here on the histogram that's labeled, and it's useful to know where the P99 is, but it's much more useful to understand the shape of this distribution. Histograms are really a great way to refine latency because you can observe different multimodal behaviors, and a software engineer can pick them out, like pick out specific modes, select them, and reduce the analysis to the mode that they're concerned with. So you can refine this histogram so that you're looking at the top 5% of requests in terms of latency. So I really encourage people to think about the shape of a distribution in addition to understanding what the P99 latency is. It's much easier to like identify different modalities in the distribution and drill into those when you're trying to understand the regression. So finally, we are here on the scorecard for refinement. Here you can see that cardinality is also important in the scorecard for refinement, arguably more important than in detection. And we also, once again, need to understand how much money we're spending for the tag values. That's fairly important here as well. It's also important to have robust statistics, and in my mind that means that we should be using histograms. And it's pretty important because it allows you to quickly reduce the entire set of your hypotheses, and it allows you to, for example, look at the top 5% requests. So that's a really nice thing to refine. The next thing here is it's important to understand how long your data is retained for, because usually when you identify a regression, like one of the first questions that I ask is this a new regression or has this been happening for a while? What's normal? And having retention horizons that are quite long help you answer the what's normal question. So it's important that you can look at a regression and see the exact same regression or metric essentially 2 hours ago, a week ago, etc. So you can easily answer the what's normal question. A lot of time series data try to answer the what's normal question, but I think there are better ways to do this in the future. The other part of the refinement scorecard is explaining variance. So once again, correct statistics is really important here, and there's a lot of inaccurate statistics out there, so just make sure that you're looking at correct statistics while you're performing the refinement activity. And the last thing to discuss on the scorecard is the suppressing of messengers for microservices failures. So in this diagram here on the right, you can see that there is a top service that depends on an intermediary service, which depends on a tertiary service. And if the tertiary service fails, you don't want to blame the intermediary service for that failure. The intermediary service will still indicate a failure in its own performance, but it's not the true culprit here. So you shouldn't waste any time debugging the intermediary service. Instead, you should have an observability system that quickly suppresses the intermediary surface, so you can quickly refine the search space and identify the services that are actually causing the problem, not services that are being affected by the culprits. Cool, so wrapping up, it's a pretty fun game to try to design your own observability system. So if you want to have high throughput, high cardinality, a lengthy retention window, and you want something unsampled, so ideally you can have all four. But realistically, we can't really build for all four. There's a lot of different observability tools that can approximate these four properties, but at the end of the day, we can only choose 3. And that's the essence of the problem, and that's why there's so much activity in the observability space. So the last thing I wanted to discuss quickly is that I really think that the tracing data is the best data source that we have. Obviously, I'm biased because I work on a tracing product, but it's so much more useful than logs and metrics, and I found it really integrates well with my workflow. It's a superset of log data for transactions, and it really is valuable in suppressing different hypotheses. Specifically, it can help you quickly identify which parts of the system are actually reflecting the failures, not necessarily the parts of the system that are being affected by the culprits, which is what I was describing earlier. So that's pretty useful. But the main problem here with tracing is that the retention is like quite killer. So, you know, us retaining 1 out of every 10,000 transactions is fairly problematic, like I mentioned earlier, especially in identifying that needle in a haystack. So there are some other approaches where you can retain 100% of the data for some period of time, and you can sample from that data set and explain some hypotheses dynamically. And this is a pretty nice angle to the problem, and there are definitely other approaches to this problem, but there are ways that you can solve that, and that's what we're working on here at Lightstep. So here is a summary of the observability scorecard. I'm running out of time, so I won't dive into this in too much detail since it's fairly redundant, but that's really the conclusion of this talk. You can use a more sophisticated scorecard when you're evaluating observability technologies, and that's what we would encourage all users of observability to do. So Mitch, I think we're ready to open it up for questions.
Wonderful, Katia. Thank you so much. Great presentation. Appreciate all the information you've shared with us. Some really good questions that have come in from the participants. First question is, what's the difference between APM and observability? You mentioned earlier there's a lot of definitions about what observability is. How would you differentiate the two?
Yeah, I think for observability, it's just getting more visibility into your system, whereas APM specifically is application performance monitoring. So getting more visibility into your application performance. I think those are I think observability is like a superset of APM. Any other questions, Mitch?
Oh, sorry, I was on mute. Are there any open source components that are part of Lightstep?
Yeah, definitely. There is something called OpenTelemetry, which is essentially an API standard for tracing libraries that we follow. It's a vendor-neutral API standard, and it allows different application engineers to instrument their application code. And that's the API standard that we follow, and that's open source. And we have a bunch of tracing libraries in a number of different languages that are implemented in that. So that's the main open source component.
Wonderful, wonderful. I think if you've been in this space, you've heard about OpenTelemetry and open tracing. What dependency depth, i.e. services, should SRE teams expect real time, as in low seconds? Freshness, 5, 10, 20. It's an example they gave.
Yeah, I would expect an observability tool to give me freshness of 5 seconds at least. So 5 seconds between the time that your application emits some data to when you actually see it on your screen. If you're paged in the middle of the night, you really need to have answers as soon as possible. It's not like waiting a minute can cost a lot of money, especially if your if your website is down and you're not able to process payments. So I would advocate for having as real time of an analysis system as you can.
Okay. Next question is, would tracing, or are there situations where tracing would help detect problems in advance based on a pattern or some other things that you observe?
Yeah, I think that There are a lot of different ways that you can use tracing to detect problems in advance. Specifically, you can quickly understand if any of your SLIs are violated. So like an example of some SLIs are like throughput, latency, and error rates. And if any of those SLIs are violated, you can essentially like alert an engineer and give a bunch of example traces. So like one workflow that I've had specifically is I will get alerted if a particular operation has an error. And I use some tools to page me when that happens. But if I'm just looking at a dashboard that shows the error counts, which is essentially metrics, that's not really sufficient in a lot of cases. Instead, I kind of run into a dead end. So I'll get paged for this increase in errors. I see this chart that shows me the error count going up, but then I don't really know what to do next. And if I go to a log for that particular service, it may just show me an error that's not relevant to that service, but it's actually more relevant to a service 3 layers down the stack. And in that case, like I find that traces are extremely valuable. So if I get paged and I have some example traces where my service has those errors, I can actually traverse through the stack and quickly identify the service that is causing the outage. And so I think that like monitoring your SLIs with trace data is much more valuable because you can really understand the context a lot more quickly than you can with other solutions like metrics and logging.
Thank you, Katia. Next question, is it best to use, or maybe you can talk about the trade-offs of using one tool that gives you tracing, metrics, and logging, or should you select a tool for each? What are some of the trade-offs with that?
Yeah, I mean, obviously using one tool for all three can be easier for educating your team on just using one tool instead of several. But I think it's probably more important to like understand your workflows. And so, like I mentioned earlier, you can be either gradually increasing or improving an SLI or rapidly improving it due to an outage. And sometimes one tool won't solve all of your workflows. And if that's the case, then I would strongly recommend investing in a couple of tools that
That's our webinar mascot. Sorry about that.
Oh, no worries. In that case, I would strongly recommend investing in a couple of tools to satisfy all of the pain points that you may have. Because honestly, I feel like we live in a world that doesn't really have one solution that fits all of our needs yet. And I think it's more important to try to give software engineers the tools that they need, even if that involves more than one.
Okay, great. There was a question here about, I think someone was looking at your website, at the Lightstep website, and they're asking a question, well, how is observability different from monolithic applications versus something that's more cloud native, microservices oriented? Are there different strategies, approaches that you might need to use for different kinds of applications?
Yeah, I mean, I think the main difference is, I mean, observability was just a lot easier in a monolith architecture. Like you can use logs to understand an entire transaction because you only have one monolith. And in a distributed service architecture, it's really hard to use logs in an effective way. Like one workflow I've seen for some software engineers is they'll open up the logs for service A and then they'll see that they actually are calling service B, which is causing a problem. So then they have to go and open the logs for service B, and then they end up with all these tabs for all of these different services. So navigating through logging in a distributed trace or distributed service architecture is much more painful and it's much more expensive. So I think distributed tracing is a much more effective way to quickly like understand a regression in a distributed service architecture. So I guess the answer is observability. It was a lot more straightforward. It was still a pain in the monolith world, but it was a lot more straightforward than what we have in the distributed microservices world today. And I think we need a little bit more sophistication in our tool set. And I think tracing is a really good way to do that. And I think we still need solutions like logging and metrics, but I think that with distributed services, we need some level of tracing and some level of aggregate trace analysis so that we can like quickly identify the failure, since the number of failure modes is so much higher.
Really important point. Speaking of kind of the sampling, we had a question related to this earlier. Another question is, at what level of metric sampling does the value of metrics start to diminish? You know, is there a, you know, at some point it's beyond the point of being useful, or do you have some experience and some suggestions for that?
Yeah, I think, let me go back to these slides. I think in this case, like having this 5-second granularity is pretty useful, but then once you get into the 25-second granularity, it's really hard to identify the difference between a transient and a steady state regression. So I would say I would say like the 5-second granularity is probably the cutoff.
Okay, great, useful tip. Excuse me. How would you describe, or do you think Open Telemetry Project will build? Let me try this again. Do you think Open Telemetry Project will build out open source capabilities beyond distributed tracing to real user or synthetics? When will a Heritage API die, or sorry, Heritage APM die? Well, it's kind of a philosophical question there.
Yeah, honestly, I don't have a great answer to that question. I'm not really dialed into the OTel future plans since I mostly work on the Lightstep SaaS side of the organization. So I don't think I'm the best person to answer that. Yeah.
Okay. Well, good.
Yeah.
We're gonna have to throw one of those challenging questions, and you've done such a good job with all the others. It looks like it's probably our last question, unless anyone from the audience wants to toss a couple more out. We do have a few more minutes. Back to the question about APM vendors. How would you describe Lightstep as different from a traditional APM or traditional APM vendors?
Yeah, I think Lightstep has a lot of really interesting parts of the, or a lot of interesting value props. So I feel like we've solved the cardinality issue fairly well. Earlier, I was describing how, let me pull up the slide. So earlier, I was describing how it's really painful with tracing to only retain 1 in every 10,000 transactions. But I think the way that Lightstep has solved it is that we actually retain 100% of the transactions for a small period of time, and we allow you to do some interesting dynamic queries in real time. So I think we've handled the retention problem in tracing fairly well. And then we've also handled the cardinality issues as well. Like we essentially have a mechanism to query for high cardinality tags that isn't expensive. And lastly, I think that the traditional APM products I've seen don't have interesting aggregate trace analysis. So it's really great to look at one example trace and understand how one particular request propagates through a distributed system. But Lightstep is able to collect a huge number of traces and give you really interesting insights based on all of that trace data. And I think that's a huge value prop.
Okay, very good. We did get another question from our audience. How quickly can a tracing tool detect the actual root cause? In the example they gave, theoretical example. Let's say service A is having an issue, which is actually caused by B, which is caused by C, which is caused by A, that kind of cascading, figuring out where the root cause is. Maybe saying how quickly might be difficult, but maybe you could talk about what the process is for triaging and diagnosing that.
Yeah, I think it really depends on the issue itself. Like there are some issues that are very easy to solve with tracing, and there are some issues that still have some nuance. So maybe I can give a couple of examples. For example, with tracing, you can, let's say that you get paged because the latency of a particular operation is above the SLO. So let's say your P99 is above 10 seconds and you get paged for that. I'm not really sure what the best way to solve that with logging is, but with tracing, you can look at a bunch of example traces and see why that transaction took more than 10 seconds. So you can actually look at that visualization that I was showing you earlier. I'll get there in a minute. You can look at this visualization here, and you can see that one particular operation is contributing the most to the critical path, and that's what's causing the slowness. And you can also instrument tags and logs on different operations. So maybe you'll see that a particular tag is correlated with latency as well, or a log shows you that your service is doing a bunch of retries, which is causing the increase in latency. So you can get kind of some of this information from one trace, but I think where it becomes even more powerful is when we can take all of the traces that we've assembled and say like, hey, we've noticed that a particular property is correlated with your increase in latency. So one example of a property is like a particular region is like a US West region is correlated with the increase in latency, and tracing tools should be able to tell you that, which is very powerful. Another example is like a particular host is correlated with an increase in latency, so maybe you're having problems with one particular host. So those are the types of hypotheses that you can come up with a tracing tool. Another example is like if you're looking to identify what's causing an error in your service, it's much easier to comb through a trace and identify which service is actually originating the error and like what the tags and the logs of that particular service are. So errors, I think, are a much faster use case in a lot of cases since they're binary, like you're either having an error or you're not. With latency, I think there's a lot more nuance to it because there's just so many ways that your service can increase, or there's so many reasons why your service has an increase in latency. And I think that distributed tracing makes your hypothesis validation and invalidation much faster, which I think is the main value prop. You can like essentially reduce your mean time to resolution significantly.
Well, wonderful. I think we've come right up almost on the end of our time here, and I want to fit in a few housekeeping details. Katia, thank you for the fantastic presentation and great responses to the questions. We had some really good questions from our audience. So I'd also like to announce who our gift card winners are before we close things out here. Our 3 gift card winners are G. Gutman, K. Mum, and P. Cope. The folks here at DevOps.com will reach out to you about how to get a hold of those gift cards. Just a reminder, we're sending out an email with a link to the recording and to the slides, and also a link to the sandbox so you could try out the product. Be sure to check out DevOps.com for other great webinars that we have coming up with Lightstep and with others. It's been my great pleasure to host the webinar today, and I'd like everyone to join me in thanking Katia Bazzi, who is software engineer with Lightstep. Fantastic job. Again, we got some great feedback from the audience too about your presentation. And of course, we'd like to thank our audience for spending your time with us, spending a whole hour with us on a webinar. We know your time is super valuable, and we're honored that you would spend it with us. It's been my great pleasure hosting. Hope everyone has a great day and be careful out there.
Thank you.